comments and questions about his presentation. In the bottom left corner of your screen, you have a chat window. It says, please type your comment here, and that's exactly what you do. There is no send button. The message is sent the moment you hit the return key. If you have a question during the presentation, please type away as soon as it pops into your head. I will collect the questions, and Dr. von der Heydt will answer them at the end of his talk. So now that we are comfy with the technical details, let's get back to content. Hydrogenious was a finalist at the ACHEMA-Gründerpreis. This startup award was installed on occasion of ACHEMA 2015 and featured companies or companies to be in the categories energy, industrial biology, and analytics. ACHEMA-Gründerpreis is organized and supported by ACHEMA, the expert network for chemical engineering and biotechnology in Germany, by High-Tech Gründerfonds as a venture capital organization, and by Business Angels Rhein-Main. The Business Angels provide not only venture capital, but also mentoring, consulting, and a huge network to bring ideas into the market. If you are a startup company or just in the midst of writing a business plan, you can take part in ACHEMA-Gründerpreis 2018 until November 30 this year. Now to our finalist, Hydrogenious. There's no way around hydrogen as one of the most important energy carriers of the future. A simple internet search shows the huge potential in terms of fuel, for example. However, hydrogen does have some serious challenges, and being explosive is just one of them. Hydrogenious has found a very ingenious way to deal with these challenges, and I am happy to introduce Dr. Cornelius von der Heydt, Head of Marketing at Hydrogenious. He holds a PhD in business science and also has several years of business consulting under his belt. I'm very excited to hear what has happened at Hydrogenious in the last 2.5 years since the company took part in ACHEMA-Gründerpreis. As already said, if you would like to ask any questions to Dr. von der Heydt, please type them into the chat window. I will collect them and present them to Dr. von der Heydt after his talk. Herr Dr. von der Heydt, thank you for taking the time to hold this presentation. The floor is yours.
Well, thank you very much. So I hope that everybody can see the first page now. If not, please somebody let me know. Welcome everybody also from my side. My name is Cornelius von der Heydt from Hydrogenious Technologies, and we have invented a form of hydrogen storage that is called liquid organic hydrogen carriers. And as Marlene said, we're one of the finalists at the ACHEMA-Gründerpreis 2015. And of course, since 2015, especially in our startup, a lot has happened. But let me maybe first come to the overall challenges that we as Hydrogenious address. So there is a very intense discussion, especially over the last few months in Germany, Europe, and I would say globally, with regards to decarbonization of basically of the world, you could say, with Dieselgate in Germany, and there's actually the diesel ban under discussion in German cities. We have huge issues in China. We have the whole debate with the Trump legislation in the United States. But there are targets which most countries globally have committed to under COP21, for example. There are EU emission reduction targets by 2050, which says 80% CO2 emission reduction compared to 1990. That usually is by 2050, mobility minus 60%, and energy minus 90%. And the question is how actually to do it. And hydrogen, as actually the most versatile energy vector in the universe, will play and will have to play a very important part in this whole setting. There's on the industrial side, hydrogen is actually the second most commonly used gas in industry, but it's today produced to 99% from methane cracking, so emitting CO2. Replacing this with green hydrogen will have a huge impact on industry, especially on chemical and petrochemical industries, of course. Mobility, there is currently, I would say, the battery electric mobility has a slight advantage in public perception, but there are significant activities in the fields of passenger vehicles, but also especially in the fields of buses, light-duty vehicles, trucks. Alstom has developed a hydrogen train, and hydrogen will have to play a very, very important aspect in decarbonizing the mobility sector, mainly in let's say, larger scale mobility applications. And of course, energy. We are in Germany, for example, already we've gone quite a nice way in turning our electricity supply or energy supply to renewable energies, but to really reach a share that is above 50 or 60%, we're today at roughly 33%, that will need also large-scale energy storage, which will have to be in some form a chemical storage, and there hydrogen is also an ideal vector. But hydrogen has the big problem that it is not only the lightest molecule in the world, it's actually also highly explosive, and that was very, very difficult to store, to transport under high pressures is very inefficient. Now that brings us to the big question: if you want to connect those dots, renewable energies and basically decarbonizing the world by bringing it from a fossil economy to an electricity-based economy, how can you actually connect those dots, connecting the renewable energy sources to industry and especially to mobility? As mentioned, the hydrogen technologies, as they're used or as they're in operations and application today, are typically compressed hydrogen at up to 500 bar for road transport. The standard is somewhere around 250 bar. Those are very, very high pressures, but still, even at those pressures, the storage density on board of trucks and trailers is still very, very limited. Alternative is cryogenic hydrogen, cooling it down to minus 253 degrees centigrade, which is a highly energy intensive process. You do have higher storage capacities on a trailer, but the trailer costs you €1 million to €1.5 million. And in both cases, are you dealing with a highly explosive and flammable gas, which is handleable and can be handled in a industrial setting. So the large industrial gas companies of this world today are able to handle that in this setting with trained people. But if you think about bringing that out into public, basically, to public refueling stations, to public wind parks and PV parks to produce the green hydrogen, then those are not technologies where we can actually imagine that could in somehow work. But I mean, we are used to a liquid transport system, and why not continue using a liquid system? And that is exactly what we have invented here at Hydrogenious. That the liquid organic hydrogen carrier technology does nothing else but enabling to carry a liquid instead of a highly flammable gas at either elevated pressures or very low temperatures. Now, how does it work? The process from a chemical perspective is a reversible hydrogenation and dehydrogenation process. It's both are catalytic processes. In the hydrogenation, on the left-hand side, we call the hydrogenation plant a storage box, because it basically stores the hydrogen. We have hydrogen that comes in at 25 to maximum 50 bar pressure into a hydrogenation reactor, and there it is comes into contact with a catalyst and with a carrier liquid. The carrier liquid that we use is widely known in industry under the brand name Marlotherm. Chemical name is dibenzyl toluene, and this actually is a carrier liquid, I'll come to it in a second, that is already used today in large amounts. Then what you have is an oil that you can store in the fossil or in the infrastructure of fossil fuels as it is already existent today, which is today used to transport diesel or gasoline. And then you have the dehydrogenation, which we call the release box, where the hydrogen is released again, and you can reuse the carrier liquid, which is then called LOHC minus, basically because it does not have hydrogen on it anymore, and then can be used in a circular economy, basically. So it's very important that the carrier liquid is not consumed; is really just a carrier. Now, from a let's say a more technical perspective, which I'm sure a lot of the people in this call are interested in, as already mentioned, it's a catalytic process. Both processes are catalytic. The hydrogenation at 25 to 50 bar, an exothermic process at roughly 250 degrees centigrade, where the hydrogen reacts at the catalyst with the carrier liquid. The carrier liquid is an unsaturated hydrocarbon called dibenzyl toluene. It's basically 3 toluene rings. And as you can see on the top picture, that's actually how we store and transport hydrogen in the Marlotherm today. You can see that it is slightly orange, reddish. That is actually also the color when it is not hydrogenated. It's somewhere in this orange-ish color range. And then when it is hydrogenated, so has been saturated with hydrogen, you have perhydrodibenzyl toluene. And as you can see at the bottom, you have a clear IBC there that is actually filled with 1 cubic meter of LOHC, and 1 cubic meter of LOHC can store up to 57 up to 57 kilograms of hydrogen at ambient conditions. The dehydrogenation process then is an endothermic process, so it's actually the corresponding process from a chemical perspective to the hydrogenation. The same amount of heat that the exothermic reaction at the hydrogenation releases, you have to insert at the dehydrogenation site at a temperature level of roughly 300 degrees centigrade. And then the hydrogen is released at a pressure of 1 to 3 bar absolute, so we typically compress it, and then it can be used in industrial processes or for mobility applications where we see a lot of potential going forward. That is let's say the circular unit or the circular perspective on a more technical basis. Now, the big advantages of this technology compared to existing technologies is, on the one side, the storage density. The LOHC has a storage density of 6.23 weight percent. I already mentioned the 57 kilograms per cubic meter. That actually is comparable from a volumetric storage density to pressure storage at over 2000 bar pressure, because hydrogen is a gas that behaves very non-ideal in elevated pressures. So the storage density does not really increase with increasing pressure levels. It is very easy to handle, as already mentioned, as a diesel-like liquid at ambient conditions. So you can open the tank, and I'll show you a small video briefly on how we actually, if you don't treat it too nicely, what happens or does not happen to the carrier liquid. And most importantly, it is very low priced. So already today, in the small quantities that we buy it at for our systems here, we pay less than 5 euros per kilogram. And if you basically set up a larger scale infrastructure based on LOHC, the prices will go down to somewhere between 2 and 3 euros per kilogram. And that translates to a hydrogen storage price of somewhere around 50 euros per kilogram of hydrogen. And that is comparable, if you compare it to today's costs of storage capacity, you are, for the low pressure, so talking 30, 50, maybe maximum 100 bars compressed storage, you're somewhere between 200 and 500 euros per kilogram storage capacity. And for high pressure storage at 500 bar and above, you're at 1,000 euros per kilogram of storage capacity, just because the materials that need to be used for those elevated pressures are expensive, and therewith the whole capacity basically becomes expensive. Now, as a few of you, or a lot of you in the call might be familiar with REACH registration, and that is, besides the whole safety in terms of non-flammability, non-explosiveness, and the advantages on storage density, we have registered this liquid loaded with hydrogen under the European registration REACH, and it is not classified as a hazardous substance, so it's not classified as a dangerous good according to ADR and all the other transport regulations. And it is not fish toxic, for example, so it's very safe and easy from a handling perspective. And that is another very strong also cost advantage in terms of operational cost, because you are allowed to drive through tunnels without any problems. That with compressed or molecular hydrogen that differs a little from country to country actually. You can transport it on trains and on ships without any problems, and therewith actually reduce the cost of transport of hydrogen even further than it is already being reduced just through transporting it in a normal diesel trailer. So that is on the let's say the regulatory side, and I promised you a little video that is on the safety side of our hydrogen. So we've taken a few months ago we've taken our best looking intern to test a little bit in the kitchen. What you can see here on the right hand side, what he currently where he's now, that's hydrogen, or that's LOHC loaded with hydrogen. We actually store it like that in a normal plastic IBC. And there again you can see the difference in color from transparent to orange-ish. So that's the unloaded liquid. And then we have sent him to a little showroom kitchen and to torture the material a bit. Now everybody can imagine what would happen if you do that to a molecular hydrogen source in whatever way. That's not necessarily recommended. The flaming point of this of dibenzyl toluene actually is somewhere around 55 degrees centigrade, so even significantly above the flaming point of diesel, for example. And as you can see here now with that Bunsen burner, as soon as he takes it away, the liquid does not burn or anything. And we have actually managed to enlighten the liquid at some point. It takes quite a while, but then once it does actually burn, you can actually blow it out like a candle. So even from if it actually burns, it is very easy to extinguish. Now, the most important aspect, however, is of course the cost side. Does it actually bring a cost advantage? And yes, it does. What you can see here is the cost structure of a typical hydrogen delivery. In this case, for 300 kilometers, that's kind of the maximum that is somehow viable with today's technologies. And as you can see, especially for compressed hydrogen, the cost of transport is actually by far the biggest cost block in this whole equation, and that is because the storage density of hydrogen on those tube trailers is so low. A typical 250 bar hydrogen tube trailer can actually only carry roughly 350 kilograms of hydrogen. That means you're actually driving around with 99% steel. Those 500 bar trailers, they can store up to 1,100 kilograms of hydrogen, but because the pressure is so high, you actually have to have very special carbon fiber tube trailers that cost you somewhere around 800,000 euros just the trailer. And you're still not at the up to 1,800 kilograms that we can reach with LOHC, and that you can transport in a normal, very cheap diesel tank trailer. So besides all those operational and safety aspects, our technology will also bring a cost improvement to the hydrogen delivered, for example, to an industrial consumer or a hydrogen refueling station. So that is, in a nutshell, and very briefly, our LOHC technology as it works and what it brings. Now, of course, the question is, who are we? where Hydrogenious Technologies, founded in 2013, a spin-off of the University of Erlangen. And we're basically the result of research that has been conducted at the university since 2009, initially in a joint research project with BMW on the liquid organic hydrogen carrier technology. And by now, with over 25 patent families filed globally, 5 of them have actually been granted already. We do consider ourselves to be the global technology leader in this LOHC field. There are other companies also working with LOHC. There's Chiyoda and Hitachi in Japan. There's a company in China, but they all use different carrier materials, which from our side or our perspective have significant drawbacks in terms of toxicity, flammability, pricing, or cost of the carrier, hydrogen purity, easiness to handle, and so on. We have been able to develop very high-class partnerships, for example, with Clariant, the catalyst manufacturer. As I mentioned, both processes are catalytic processes. Sasol is the producer of the carrier liquid, which is the brand name, as mentioned, is Marlotherm, because it is produced in Marl in Germany, and it's a thermal heat transfer oil. Anglo Platinum, the largest platinum group metals mining company in the world, is actually our investor. They have a general interest in hydrogen technologies because hydrogen technologies typically consume or use somehow platinum group metals. And MAN, for example, there we're not working with the engine or the truck manufacturing departments, but with the Deggendorfer Werft, which is a world leader in large-scale reactor manufacturing, especially for chemical and petrochemical processes in larger scale, which we see as the target setting for our technology and the target application. We have the first systems in operation actually since May 2015, the part on the left-hand side, and since June 2016, the part on the right-hand side that you can see on this slide. So the overall end-to-end setting, starting with a nearly 100 kilowatts peak PV system that where we can use the green electricity to produce green hydrogen in our own in-house electrolyzer from Siemens, and then directly hydrogenate the liquid, and then we transport it to Stuttgart, of course not in one of those large tank trailers, but we actually use a plastic IBC in the back of a 6 sprinter. So that is how we transport 50 to 60 kilograms of hydrogen. A little side effect or little goodie on the side, we do have a kids swimming school at the front of our building, and we're actually with the exothermy of the hydrogenation process and also a bit from the electrolyzer, we're actually heating that swimming pool for the kids. So that is a nice little side effect. This whole setting here is not a commercial setting, of course. It's a technical proof point and a technical viability proof. And the system on the right-hand side at the Fraunhofer is actually connected to a PEM fuel cell. So we do also directly show that our technology in terms of hydrogen purity released is absolutely suitable for fuel cell applications, and that fuel cell then feeds into a 600 volt DC grid for a electric car filling station. That is the system in Stuttgart, and you can basically see here in the center, that's the core part, that's the reactor that is able to release 3 kilograms of hydrogen an hour. It is connected to a PEM fuel cell with 25 kilowatts, and what you can see here on the left-hand side, that's milk tanks. That's where we store the LOHC in. That's a milk tank, just as any farmer uses it for its dairy milk and so on. This is the container is located on the top of a parking garage or parking house in Stuttgart at the Fraunhofer IAO, and as mentioned, integrated in a smart 600 volt DC grid from Siemens actually. We also do have our first commercial project underway now. It's actually being delivered in the next 3 to 4 weeks. 2 of those 3 systems, at least the third one that follows beginning of next year. Those are demonstration systems for a company called United Hydrogen Group. That's a regional hydrogen distribution company out of Tennessee. They supply a bit over 50 customers, and the application will, on the one side, be a hydrogen supply to power plants, where hydrogen is used for cooling the power generators, and the other one is steel treatment, so annealing of steel, where also a lot of hydrogen is consumed. And there, what brought United Hydrogen to do those field tests together with us under a commercial contract is actually their interest in exactly the factors that I mentioned earlier: safety, the increased transport distance that is possible because the transport capacity per trailer is actually so much more than with conventional technologies. That is an industrial setting. The hydrogen used is a byproduct from chloralkaline electrolysis, and the consumers are industrial. That is, I mean, you from the chemical industry will be aware of that. Is over $100 billion market globally, transported hydrogen, second biggest gas market in the world. So of course, for us, it's a very interesting market. However, it's also a highly sensitive market, and that's actually something that kind of started for us with the ACHEMA and the ACHEMA-Gründerpreis, because very initially that whole technology was designed and set up and thought to be most viable and the ideal solution as large-scale energy storage technology. However, hydrogen-based energy storage, stationary storage with LOHC, until that makes commercial sense, that will need another 20 to 30 years, if only once we have somewhere 70, 80, 90%, or even 100% renewables in the grid, and actually need seasonal storage. That whole market of industrial hydrogen logistics, which is on the one side a very intransparent market, it's a market that does not take place in public debate, so it's not a well-known or most accessible market, but that actually became kind of we were led to this market at the ACHEMA from all the discussions we had there with other exhibitors, but also with customers and visitors of the ACHEMA. Since September 2016, we're also part of the so-called Copernicus research program. That's the largest German research program funded by the German Ministry of Research. And there's it's basically 4 sub-programs. One is called Power to X, and in this Power to X stream, we are in the project Decentral Hydrogen Logistics, which looks into supply of hydrogen refueling stations with LOHC, and this is a very promising project for us because, as mentioned, the hydrogen or the industrial applications, they're very, very interesting for us. However, this market is very conservative. In the hydrogen mobility market, there's a big acceptance of innovation. There's a big acceptance of piloting. Of let's do it together. Let's fund the pilot. Let's just test it, which of course is not possible in a full-scale industrial plant, which is in full commercial operations. So this is let's say a first step onto the hydrogen mobility and supply of hydrogen fueling stations, and we actually have just been granted basically the second part, or a second project in this field from the European Union under Horizon 2020, a project together with 4 partners, LOHC out of Finland, a leading Scandinavian industrial gas company, is actually, let's say, the operational partner in this consortium, and there we will put one of our release box systems at a refueling station in LOHC. So the company LOHC comes out of LOHC in Finland, and the storage box, so the hydrogenation site, will be linked to a water electrolysis that LOHC operates in Finland. And with that, we can actually demonstrate the whole chain from green hydrogen out of an electrolyzer to the hydrogen in the car, and also prove that our technology fulfills all the required norms and standards and has the efficiency needed. The total duration of this project is 3 years. It's about to start now in October, so then it will go on until October 2020 with a total funding of 2.5 million euros. That is basically an overview of Hydrogenious and our activities. Maybe a word on the ACHEMA-Gründerpreis. That is basically the end of, let's say, the LOHC presentation. Maybe just a quick word on the ACHEMA-Gründerpreis from our perspective. As Marlene already mentioned, we're one of the finalists, of the 3 finalists in our sector. And even though we didn't win this award, especially the let's say the days at the ACHEMA and the discussions we had there, but also the press coverage afterwards, did bring a lot for us as a chemical energy related startup, where those networks into industry and those trade fairs and conferences and so on are always a very, very good way of making us more known to public, and also for us to learn a lot of applications that we don't have didn't have on the radar initially. And with that, I'm basically at the end of my presentation. Thank you very much for listening in, and would be happy to take all the questions that are there.
Okay, dear listeners, if you have any questions for Cornelius, please type them into the chat window on the bottom left hand of your screen. Meanwhile, I have a question, Cornelius. I'm a biotechnologist, and I was very surprised to hear that a chemical with a name such as dibenzyl toluene can be not poisonous, and basically can be something that you can have for breakfast. Because I am a biotechnologist, I know that you can do a whole lot of good with biotechnology, or you could do a whole lot of good with biotechnology if only people would let you. Biotechnology has, still somewhat of a shady reputation in some applications. How about hydrogen usage? I mean, even those who haven't paid attention in the chemistry class at school know that hydrogen is dangerous, is explosive. Even if it is stored as an LOHC, do you know anything about the general public perception of hydrogen technologies?
There's, of course, as I mentioned also, from my perspective, batteries, for example, have a lot. On the one side, the industry is doing a better job than the hydrogen industry in marketing itself, and they have a better standing in public perception. With hydrogen, there's kind of 3 general public perceptions from my perspective. One is people think about the Hindenburg and say, oh, it's dangerous and explosive, and that is even though hydrogen is actually a lot safer than today's gasoline, for example, because if you have if you're not in a tunnel but in open space, it is actually very difficult to ignite hydrogen, and because it is so light and goes away so quickly. But that is the general, from my perspective, the general perception of people who are not so keen on dealing with gases, with flammable gases especially. They prefer to handle a liquid. So there's a public perception hydrogen is dangerous. The second aspect is it's there in 5 years. That's kind of a standard phrase in hydrogen technology development. We'll be there in 5 years. That was the saying in 1985. That was the saying in 1990, and so on. It has continuously improved, but so have, of course, other technologies. So the competition has become harder and harder. And I think what we have seen now with all those discussions on electric mobility and so on, there there still will need to be, but there also already has been a strong push towards those electric drivetrains, where hydrogen is one part of it. I mean, hydrogen is also an electric drivetrain in the end. And the third perception is it's too expensive. There's too much platinum on the fuel cell or on the electrolysis. It's inefficient because the electrolysis only has 70% efficiency, the fuel cell 50. But I want to use if I'm interested in the electricity, then I use a battery. That's why I also say energy storage in terms of electricity storage is a market for hydrogen only in a couple of years' time. But if you need hydrogen for a chemical process and you want to decarbonize this process, you actually need green hydrogen. And people in the end, they're not interested in efficiency, they're interested in cost. So that is not really a argument. And if I need the hydrogen and I need it to be green, then there's no other way than using green electricity and electrolyzer and producing that hydrogen. So there's still a lot of communication to be done from my perspective. There's also definitely, especially in the hydrogen mobility sector, a lot needs to be done in terms of sexiness and so on. I mean, so far hydrogen is a industrial chemical B2B market where sexiness and marketing and so on is nearly completely irrelevant. It's only about cost. But if you go into mobility, then it needs to be cool to be adapted by the public.
That sounds good. Sounds very promising. Thank you, Cornelius, for this very interesting insight into hydrogen storage technology. I think we will hear about that in 5 years and even in the long term. Our tech wizard in the background will please change presentations so that I can announce the next webinar in this series. If you liked this one, maybe you are also interested in the presentation of Gründerpreis finalist Sciomics. They will present their ScioDiscover platform, which is nothing less than a multi-tool in precision medicine. This webinar will take place on Thursday, 21st September from 1 to 2 p.m. And if you would like to attend, please register for free at www.v-b-u.org. And if you are an entrepreneur and have just recently started a company, you can still take part in ACHEMA-Gründerpreis 2018. Even if your company is not yet operating, if you are currently writing your business plan or you have just a brilliant idea for it, submit it until November 30 this year. ACHEMA-Gründerpreis is open for all topics in chemical engineering, chemistry and biotechnology, and you find the details on how to participate at www.achema-gründerpreis.de. And with that, I thank again Cornelius von der Heid. And
there's one question that I saw in the that came up.
Okay, yeah, you're right. I'm sorry. The question is, for me, the loading time and the unloading time for hydrogen sound very slow. If you release 3 kilogram per hour and the car uses about 0.8 kilogram per 100 kilometer drive, you need about 1 to 2 hours to fill one car. Excuse me if my question is stupid. I'm not a chemist or specialist, but I only want to understand if this process does make sense if you do it commercially.
Yeah, so first of all, the question is not stupid. If you would use this 3 kilogram per hour system, that definitely would not make sense. This 3 kilogram unit is the smallest unit that we that will ever make sense commercially, but not on a mobility, not for a refueling station, but for chemical processes where you have kind of that consumption on a steady basis. The target, so the storage plants, they will be very, very large scale with several tons an hour in the of hydrogen storage per hour in the target setting, in line with today's industrial applications. And even at the last Hanover Messe, for example, all electrolysis manufacturers actually presented their concepts for multi-megawatt electrolyzers in the 20, 50, 100 to even up to 400 megawatt electrolyzers, which is then really several tons of hydrogen per hour. On the refueling station side, if you think about mobility, you have to differentiate between the bulk storage part and the so-called high-pressure cascade. The high-pressure cascade compresses the hydrogen up to either 350 bar or 700 bar. That's the target pressure in a car, in a passenger vehicle, or in a truck. A truck has 350 bar. And there, the actual dispensing into the car only needs 3 to maximum 5 minutes, and then you have a load of your tank that can drive you 500 kilometers now. Hyundai is coming out with a new car, I think in October now, that can actually has a range of 800 to 900 kilometers with one filling. And for those applications, our target scale for our release box systems is somewhere in the range of 100 kilograms of hydrogen per hour. That would give you enough hydrogen to refuel roughly 100 buses per day. So it's just a question of how big you scale the systems, the capacity of the systems.
Mm-hmm. Thank you, Cornelius, for this, for elaborating on this question. The listener who asked this question also thanks you, as do I, and I also say thank you to all the listeners out there. And with this, I close this webinar. Thank you for listening, and have a very nice rest of the day.
Thank you very much. Thank you. Bye-bye.